Good morning, everyone. So I think let's just get started. So last part of the workshop, we talk about population, right? We talk about sample. We talk about how can we collect samples, right? And what kind of data types are there. So for this part, today's workshop, I'm going to just formally start describing statistics, right? The necessary components to perform a statistical analysis. So I will talk about the probability and the distributions as well as part of the hypothesis testing, which is confidence intervals. Um, so again, there were case studies. So if you are interested, you can take a look at these three papers yourself. But let's start with the probability and distribution. So before we talk about that, we probably want to understand several definitions so that you will know when you are going to use probabilities, right? When you need to use distributions and what type of distributions you are going to use. So there were different definitions. So the first one is population, right? So we talked about population before. So population meaning that it's just the entire collection of the elements, right, that you are interested to study, right? And then the variable meaning is a characteristic that takes different values for different elements in that population. So from this definition, right, variable, can you give me an example where we can call something as a variable? Well, obviously the variable is associated with population, right? Probably you want to define population first, then you can define a possible variable. Independent, dependent. Can you say it again? Independent. Yes. So this is once I define a variable, right? There are properties of those variables, right? For example, two variables can be independent, and those two variables can be dependent, right? But I guess my question is that can you give me a concrete example? For example, what this variable can represent? Like quantitative. Yes. Yes, the variable can be continuous, can be categorical, right? For example, if we are interested in studying HIV population, right? So we could say this variable being the treatment outcome, right? Something like that, yeah. While corresponding to the population, right, there's the random sample. So we talk about sample, right, because it's hard for us to collect all the elements, right, from the entire population. So we have to take sample from the population. And more importantly, we want to take a random sample of the population, right? Because we hope this random sample can be a representative, a subset of the population. And this random sample could be more manageable, right? Because it's a smaller sample size. And so that's why we call this as a random sample, right? And again, right, that means if I follow the random sampling procedure multiple times, right, what does that mean? That means every time the sample I collect is highly likely to be different, right, each time. Well, there may be like overlap, right? But if you look at the entire sample, that can be different, right? So this is why this randomness comes from. This is really from the random procedure to collect the subset of the elements from the entire population. And then the corresponding concept, right, together, just like when you talk about population, you want to, well, obviously the population have different characteristics, right? What is the primary variable of interest, right? So this is the variable we are talking about. And corresponding to the random sample, then we have the random variable, right? Again, if you're comparing the definition of variable and the random variable, they are similar, right? It's just the one is corresponding to the population, and this random variable is corresponding to the sample, right? Again, why we call this as a random variable is that, well, if you repeat this sampling procedure multiple times, right, the variables you are looking at, the value will change, right? So it's random. And so the next concept is called sample space. What do we mean by the sample space? Is a set of all possible outcomes of a random variable, right? So, for example, going back to our previous example, if I define the variable being the patient outcome, right? So, what's the sample space? If we are using binary, then the sampling space is either success or not, right? 0, 1. This so all the possible values, right, for that the variables can take is the sample space. And then once we define the sample space, we can also define the event. That is the subset of interest of the possible outcomes in the sample space, right? So again, connecting to the previous example, if our variable is binary 0, 1, so the event could be what's the chance that people is actually responding to the treatment, right? Which is the variable equals to 1, right? So this is a subset of the sample space. And then the probability, right? This random variable or the outcome, the sample falls into that pre-specified event. Okay, so let's maybe look at some case studies so that we can better understand those concepts. So here, for the case study number 1, so this is what is described to the population. That is a treatment-naive persons aged 18 years and or older with HIV RA levels greater than 1,000 copies per ml without resistance to nucleoside reverse transcriptase inhibitors or protease inhibitors. So this is sort of like all the people, right? The treatment naive people where the age has to satisfy these criteria, right? And what's the variable they are interested is the change in LDL cholesterol after HIV treatment. So this is a variable. And what's the corresponding random sample is that, okay, among all this, everyone in this entire population, I'm going to randomly select 300 individuals. So what's the sample size? 300, right? Okay. And then what's the corresponding random variable? Well, again, the random variable, well, is defined similarly as the variables, right? The change in LDL. And also more specifically because they are going to do a clinical trial, right? So they have a more concrete definition while the change is actually from week 0 to week 24. And more importantly, we are going to only measure the change in those 300 individuals, right? We are not going to make changes for everyone in the entire population. So this is the definition of our random variable. And what's the sample space, right? So the sample space meaning that it's all the possible values, right, that the change in LDL can take, right? So obviously, right, theoretically, for any changes, right, because first of all, the change is continuous, right? It's not categorical, it's not binary, right? So theoretically, the change can be from negative infinity to infinity, right? But what's the practical, I guess, sample space for that? Anyone knows? Well, I don't know. I mean, but obviously, right? You have to sort of like understand the difference between theoretical and the practical, right? Obviously, sometimes, right? Even though we sometimes know the distinction between theoretical boundary and the practical boundary, right? But in terms of later on the modeling, right? So how can we describe this random variable? Sometimes those theoretical range may be much easier to model, right? Just so you know, there are differences, but sometimes, right, even though people understand there are differences, but again, in terms of modeling convenience or theoretical convenience, they choose to use theoretical boundaries. So you will see later why we say it's more convenient because there are like distributions available to describe, the boundaries between negative infinity to infinity. Okay, so once we have this sample space, right, then we can define events, right? So the event being the change in LDL should be greater than 10, right? So this is sort of like, even though my boundary is from negative infinity to infinity, but I'm more interested in the people like who the change is actually a positive number, right? And this positive number is greater than 10. Okay, then according to this event, right, the probability will be what's the chance that this event will happen, right? So for example, if my event set being someone chosen at random will have a change equals to negative infinity, right? So do you know what's the probability of that event will happen? I would say that's 0, right? So right, it's rarely happens, right? So I guess then this associated with probability. What's your understanding of this probability? So you probably have handled with probability all the time, right? You talk about probability and what's your definition of this probability? The number of possible effects over the number of possible events. Okay, so okay. So the small number, what does the small value of the probability mean? A lower chance. A lower chance, less likely to happen, right? The higher the number, meaning it's highly likely to happen, right? So what's the value that the probability can take? The possible like range. 0 to 1. Yeah, 0 to 1, right? 1 means it's going to happen 100% of the chance, right? So it's going to happen. So it will happen. And 0 means it's never going to happen, right? So what's the event I described, right? The people that will have a change being negative infinity, right? So in practice, probably this will never going to happen, right? So the probability will be 0. So this event, right, will never going to happen, right? On the other hand, right, so what if I specify the event, right, being someone chosen at random will have a change in LDL between negative infinity to infinity? What do you think of the probability that event will happen? Yes, right, because it covers the entire sample space, right? So it's 1. So I guess this example also, I guess, hopefully give you some ideas in terms of what event you are going to choose, right? How to specify. Sometimes you can always specify an event that you can always get a result, but whether this event will give you any meaningful, the understandings, right? It's another question. Okay, so I will talk about this into more details later. Okay, so let's look at another exercise. So here, this also defines a population, HIV infected patients at this location, right, from year 2005 to year 2009. And the age range is 15 years and older. So this is how they describe the population. And then this variable of interest is virologic control over follow-up. And the random sample is that they are going to randomly select 320 individuals from this entire population. Okay, so what's the random variable from this random sample? Does HIV already happy per milliliter in that cohort in 300 individuals 15 years and older? You mean HIV RNA, this copy? This one? So this value for this randomly selected 320 individuals, right? Okay. Anyone else? So less than 50 copies in 320. Okay, so the first answer is HIV RNA, right? The second answer is including all these definitions, right? I have this HIV RNA, but I also want to see whether this HIV RNA is below a threshold. Which one? Below a threshold. Right. So I guess this is basically this is a definition for this virologic control, right? So basically, this virologic control, that means we look at this HIV RNA and to see whether it's below this limit, right? Okay. Then now, given we now better understand the definition of virologic control, so what's the sample space for the random variable? Binary, 0. Yes, 0, 1, right? Yes. So this is the sample space is binary, 0, 1. So if we don't have, right, so for example, instead, right, the variable will be HIV RNA, right, instead of having this constraint. So what would be the sample space? 0 to infinity. Yes, right. So this is 0 to infinity. Yeah. So this is very important, right? Even though this is a continuous variable, but if you have a constraint, then the continuous variable, right? So by looking at everything together, this actually becomes 0, 1, right? So sometimes this is another trick, right? When you do the statistical modeling, right? You can always truncate, right, the continuous variable into binary or categorical, right? Just by having those criteria or the limit. Okay, so now once everyone better understand this population variable event probability, so now let's talk about the distributions, right? A random variable, right? Again, the definition is that it's a characteristic that takes different values for different elements in a sample. So remember, that means, right, we can actually have multiple random variables, right, for the same element, right, the same sample. You can have random variable A, random variable B, etc., right? So when you have multiple of these random variables, then previously what you said, independence, dependence, right, this is how I quantify how the relationship among those random variables. Just to let you know, there's not always only just one single random variable, right? But then this concept, you will learn this concept in the later part of the workshop. So now just look at a single random variable, right? For now. Okay, so in statistics, people probably typically use these uppercase letters, and typically they use X or Y most often to describe a random variable. So if you have multiple random variables, they will just say X1, X2, X3, etc., right? And but here, because we are only talking about just one random variable, so we either use X or Y, right? So again, right, because the random variable will take some values, right? So the values can be, remember in the first part of the workshop, we talk about there are different types of these numbers, right? They can be discrete, they can be continuous, right? The same thing. Whenever you have a random variable, the first thing is that to understand what's the type, right? What's the value that this random variable can take? Because this actually, the values, right, that random variable can take will make us to decide which is a more proper probability distribution to describe this random variable. So, for example, the random variables can be discrete, right? Within the discrete, it can be either binary or categorical, right, or ordinal. So, for example, the hospital remissions after initial charges, right? So this is 0, 1, 2, 3, which is countable, right? The counts, right? And then the one we just talked about, virologic control, which is binary, right? And then we can also have the random variables being continuous, right? The easy thing is the age, the BMI, the weight, the height, right? And then the change in LDL and some time to survival or recovery time after surgery, right? So those are the continuous random variables. Okay, so first of all, in the bigger category, right, whether it's discrete or continuous, then we actually have two broader type of distributions, right? For the discrete random variables, the probability distribution is typically called the probability mass function. So, which is a function that maps every possible value of a discrete random variable to the probability of that value. And correspondingly, to the continuous random variable, this is called the probability density function. Well, so instead of just a function mapping the mass, right, to the probability, and then this probability density function is typically a curve, right, that specifies the probability. And for that curve, this probability is typically the area under the curve. Okay, so those may be very discrete abstract. So let's just look at specific examples. And so I use F to denote this is a function, right? And more specifically, this is a probability max function. And this big Y denotes this is the probability max function specific to the random variable Y. And then this small y is actually the realization of this big Y. Okay, so first of all, the property of being a probability is that the probability has to be within 0 to 1, right? And then the sum of all these probabilities, right, over all the possible values that this random variable can take has to be equal to 1, right? Just going back to the previous example, right? What's the entire sampling space, right? Is all the possible values that this random variable can take. Then what's the probability that this random variable falls into this is 1, right? So this is how I going back. One of the probability, the characteristic that probability mass function or the probability function has to satisfy. Okay, so the discrete random variable is typically sometimes easier to understand. So here, this is the example. So here is our population. It's all the babies born at Duke Regional Hospital. And what's the variable I'm interested? It's the number of babies with blood type O, right? And then what's the random sample? I'm going to randomly sample four babies out of my entire population. So here I use big letter Y to denote the random variable, right? And what is random variable? Which is the number of babies, right? Out of 4, because this is my sample space, right? The sample size where I only have 4 babies. So the number of babies out of 4 with type O blood. And then this is the PMF, the probability mass function, specific for this random variable, right? So first of all, are these properties, do these functions satisfy the properties of being a probability mass function? Is this a valid function, I guess? So the criteria is there are 2 properties, right? You have to satisfy. So first of all, is this for all this possible realization of this random variable Y? Okay, so first of all, given the definition, what is the all possible realization of this Y, which is what's the sample space for this Y? What's the possible value that this Y can take, basically, right? Well, the definition of Y is the number of babies with type O blood. 0 to 4? Yes, right, because the maximum, because I'm only going to sample 4 babies, right? The maximum is that all these 4 babies actually have this specific blood type, right? So this is 4. The minimum is that none of them have this particular blood type. So this is 0, right? So that's why if you look at this function, the sample space, right, is from 0 to 4. And then this function, right, this small r function actually maps this value to a probability, right, to a number, right? So the first question is that, is this a valid probability mass function? Yes, right, why yes? So first of all, if you look at all these probability numbers, right, are they between 0 to 1? They are, right? They are above 0 and below 1. None of them are negative, right? None of them are above 1. Okay, the second one is that you have to sort of like do the summation, right? Just sum all these 5 numbers together to see whether they equal to Y exactly, right? So if they don't equal to Y exactly, that means this is not a valid PMF, right? So always you have to check, right, whether to see whether this is a valid function to describe a probability, right? What will happen, the distribution of the categorical or the discrete random variable. Okay, so now since we have determined the sample space and also the corresponding PMF for this variable of interest y. So now let's look at this following three questions. So I use this A to denote this is an event, right? So event being all four babies have type O blood. What's the probability that this event A will happen? 0.04 being the probability, right? That is y equals to 4, right? So probability y equals to 4 is 0.04. Okay. So for the second question, let B to denote the event that is at least 2 babies have type O blood. What's the probability that event will happen? Uh, 0.59. Well, how do you get this? I found the 2, 3, 4 probabilities. This one? Yes. 3. Yes. Yes. So at least 2 babies have type O blood, meaning that we are going to look at the probability that there were 2 babies having type blood, have this type O blood, and the probability there were 3 babies, right, have this type O blood, and also the probability that there were 4 babies have this type O blood, right? So basically, you are going to sum probability y equals to 2, and with probability y equals to 3, and then with probability y equals to 4, right? So basically, this is after you sum all this number together, this is the probability that this event B will happen. Okay, so now let's look at last one. Let's see to denote the event where between 1 and 2 babies have type O blood. So how what's the probability that this event will happen? Zero point 0.86. How do you get this? So sum the probabilities for y equals 1, 2, and 3. Yes. So basically, if I just get a new one, right? So the probability of this event C happens, right? Because this event C tells there's some specific criteria for this random variable being there are between 1 and 3 babies have this type O blood, right? So this event will be probability y equals to 1. So that means there's actually only 1 baby have that particular blood type, right? And plus probability y equals to 2, being there are actually 2 babies having that particular type blood. And this is probability y equals to 3, right? So this is the what we describe this event between 1 and 3 babies, right? And then we are going to look for the table to see what's the probability y equals to 1, and what's the probability of y equals to 2, and what's the probability of y equals to 3. So basically, this is all these 3 numbers add up together, right? And then if you add this up, so this gives you 0.86 chance. Okay, so basically, so my another question is so this is one way to solve this problem, right? Is there any other way to get to this probability? You can subtract the probability of 0 and 4 from 1. Yes, because we know, right, the entire sample space, right, is being 1, right? So we use 1 to minus what will be excluded from my description of this event, right? So I'm not interested in 0, right? Baby having that particular blood type. So I'm going to minus y equals to 0, and also minus probability y equals to 4, right? So those are the event that is not included into this description C, right? So I'm because sum of this everything, right, will be 1. So I'm going to use 1 minus these two probabilities, right? And which is 1 minus, if you go back, so this is 0.1, and the other is 0.04. Right, so if you copy this, again, we get to the same answer, right, 0.86, right? So basically, there were multiple ways to get to this particular probability. So the same thing, right, for this this exercise, right? So you can always use 1 minus the events, right, which is a complement of this B, right? So there were at most 1 babies, right, have type O blood. Okay, so this is sort of like what we mean by probability mass function, right? You see it's a function, it's a mapping from each of these possible values that this random variable can get, right, to a probability value, right? And again, this sum of all these possible probabilities has to be equals to 1. Okay, so once we have this define a distribution, right? So the natural thing is that what's the expected value of this random variable, meaning the mean, right? To summarize so first of all, right, we are going to use mean to summarize the center, right, of this distribution, and then later we are going to use variance to describe how spread out this distribution is, right? So if you look at this definition of this mean, so typically this mean is a population mean, and then we use mu to denote this is a population mean. The population mean equals to the expectation, and we use big E to denote this is expectation of this random variable y. And if y is a discrete random variable, then the expected value, if you look at this formula, right, this is just a summation. And remember in the previous class, we talked about when you have a data, how to do a mean. It's just you sum up all the values of this data, right? But here, because each value will occur with a certain probability, right? Then you can think of this as sort of like a weighted average, right, of all the possible values this random variable can occur. The weight is actually being quantified by the probability. That is, if this small y has a higher chance, then this value will have a higher weight to enter into the calculation of the mean, right? The mean will be closer to the value that have a higher weight. And so this is how we are going to calculate the population mean or the mean from a discrete random variable. And similarly, the variance will be a measure of the spread of all the values, right, around the expectation. So again, similarly to when you have a sample and when you data and when you want to calculate the variance, it's always the value minus the mean, right? So here, this is each of these are possible values. So here's the table. This should be I from 1 to R. So all the possible values of this y minus its corresponding population mean, right? The mean, and taking the square because we are only interested in how different, right? Instead of whether it's a smaller or bigger difference than the population mean. So that's why we take a square. And again, it's also this value is also weighted by how likely that particular value will occur. So again, after you rearrange this term, this is actually equivalent to the expected value of y squared minus the mean and to the square. And again, the standard deviation will be the square root of this variance. Okay, so going back, right, to the previous example. So here, this is our PMF. And according to the formula, right, we are going to just plug in all the possible values, which is from 0 to 4. And multiplies its corresponding probability, right, which is 0 times 0.1, 1 times 0.31, 2 times 0.36, and 3 times the corresponding probability 0.19, and 4 times 0.04. And we sum it up. This is our expectation, right, the mean. And similarly, we can calculate the variance, right? So what's this is that they're actually using this formula, right? They're using this formula to, first of all, let's go into square all the possible values, right? Which is 0 to the square, 1 to the square, 2 to the square, 3 to the square, and 4 to the square. And then they use this value minus the square of the expected value. So this is the variance for this random variable. Okay, so now let's talk about a particular useful distribution, which is a binomial distribution. So the binomial distribution is used for summarize or describe a discrete random variable. And then what's the definition of this binomial distribution? So which is what are the assumptions, right? You have to satisfy before you choose to use this binomial distribution. So again, the criteria to use this binomial distribution is that, first of all, you will have a fixed number of independent trials, right? So I use small n to denote. And so the criteria is that there's a fixed number. So that means this n cannot change according to some certain circumstances or associated with some covariance. And then those n trials have to be independent. And another criteria is that for each trial, it will be a binary outcome, which is either yes or no, or either 1 or 0. And then the probability of a success is the same for each trial. So each trial are independent and has to be identical, right? So they are going to have the same probability of getting success, denoted by pi. So a random variable y is defined to be the total number of success in these n trials, right? So just like, for example, from this definition, can you give me an example where a specific random variable can be described by a binomial distribution? Maybe this is too hard, but just look at this example. Will this example, this random variable y, be described by binomial distribution? Why?
Or you can change it into a binomial distribution as of right now. But if you really care what is, does the baby have type O blood, then it could be binomial.
Okay, so I guess my question is this y a binomial distribution? Follows a binomial distribution from the description of this binomial distribution?
No.
No? Why not?
The probability of success is something like it's something for each trial.
What's the trial in this example? Okay, so first of all, let's go back, right? Is there a fixed number of independent trials in this example? What's the small n? What's the value of that? 4. Okay. So now let's go back. For each trial results in either a yes or no.
Also true.
Yes will be type O blood, right? No will be not, right? Okay. Then the probability of success, in our case, the probability of that particular type O blood, right, is the same for each trial. Yes, right, because it's, and also are they independent? Yes, right, because the baby is assuming to be independent. Okay, so in this case, what's this random variable? The random variable is the number of babies, right, with blood O type, which is the total number of success in that 4 babies, right? So after reading everything, is this y follow a Yes, right? So this one actually follows a binomial distribution, right? So this is how you actually map the definition of the binomial distribution with this, right? First of all, you have already specified there are only like 4 babies you are interested, right? The 4 random samples. And each, according to this variable, the outcome is either yes or no binary, right? And then these 4 babies, obviously, we can safely assume they are independent. And then the chance of having that particular blood type is a constant value. So yes, this is an example of having a binomial random variable. And this is actually the PMF, the probability mass function associated with this binomial random variable, right? So here, right, when you look at this PMF, you're probably wondering how you actually get to have these probabilities, right? It's hard to, right? So this is maybe just in total 5 possible numbers. What if you get to have a larger trials, right? Instead of looking at the 4 babies, you are actually looking at the 40 babies, right? Then this all the sample space will actually go larger. And then how do you get to have all these probabilities, right? So that's why we utilize this known by the distribution function. So this is a function, if you look at this, right? This is a function actually with respect to a parameter pi, which is, well, if I know the chance for each baby, right, getting a success, if I know this, right, I can safely just plug in the values, right, to get to these probabilities, right? So this is the parameter. Yes.
So I'm not super used to this type of information, but like how do you interpret the residues and why?
Oh, okay. Yes. This is a good question. So how to understand this, right? Basically, so for example, let's just say small y is a one realization that this big Y can take, right? Let's go back to our example, right? Our example is that suppose we have 4 babies, and so if y equals to 0, what this means is that none of the babies will have that particular blood type, right? And then how to calculate that probability, right? So this is going back to this formula, how to calculate. So first of all, if y equals to 0, that means none of the babies will have a success, right? The pi, right? So if you look at the pi to the power of 0, what's the value? 1, right? So for example, if I just say, is it 0.5 to the power of 0, right? So that's just 1, right? Any value, right? Obviously, because this is a probability, right? Any value to the power of 0 is 1. And what's left? What's 1 minus pi?
0.75.
Oh, no. What's the meaning of 1 minus pi?
1 minus the probability of success for each trial.
Yes, then what's the value for? How do we understand 1 minus probability of success?
Probability of not success.
Yes, a failure, right? Because we know for each trial, the sample space is only either success or failure, right? So if pi, for example, if pi is the probability of success, then 1 minus pi will be the probability of failure, right? Because pi plus 1 minus pi equals to 1, right? The total sample space is either a success or failure. So the chance of success and the 1 minus pi is the chance of failure. So that's why we have 0 trial having the success. So pi to the power of 0 will just be 1, right? Will not influence this probability. So what's left is the chance of failure, right? So it's 1 minus pi. And then this n is the total number of trials, right, which is 4 babies, right? Maximally, you can always get a 4 success. But here, because we are unlucky, the total number of success is actually 0. So that means 4 minus 0 means that all those trials, they actually have a failure outcome, right? So this is what's the failure outcome, right? So this is well, what's the probability you get failure, right? So which is 1 minus pi, right? So this is one failure, and times 1 minus pi, so this is another failure, right? And 1 minus pi, this is the third failure, and then 1 minus pi, right? So this is equals to 1 minus pi to the power of 4, right? And okay, what's more important is this, right? So this is called n choose y. So why do we need to have this n choose y? So this is well, obviously this is not a good example because we know if zero success, that means all these trials will result in failure, right? And what if my question is that what's the probability of y equals to 1, right? So y equals to 1, what's this n choose? So that becomes, let's just say n choose 1, right? So what's this n choose 1? Meaning that, well, obviously I know there's one success in these 4 trials, right? But I don't care which trial got me a success, right? So what's the possible choices of having a total number of success in these 4 trials? Right, the possibility could be the first trial is a success, right? Or the second trial is a success, right? But everything else is a failure, right? A failure. Or the third trial is a right, but everything else is a failure. Or the fourth trial is a success, but everything else, right? So the 4 choose 1 actually equals to 4. That is, there are 4 different type of scenarios, right? But then they all result into this single variable. That is, the total number of success is 1, right? So this is why we have this n choose y in front of that. And once we know how many how many choices, right, result in the pattern of the trials being success or failure, right, result in this total number. We just multiply the success rate, right, powered by how many success trials, and the failure rate powered by how many failure trials. Does that make sense? Yeah. Right, so this is how you understand this probability mass function. And again, right, once we have this nice formula, again, if you derive this formula, right, so we know the expectation is n times pi, that is the total number of trials, and times the probability of success. And the variance will be the expectation times the probability of failure. So that's why we want to use some known distributional function, because otherwise, if we don't know what this distribution follows, right, you have to do all this math, right? You have to, sorry, here. You have to plug in all the values here, right? Where is it? Oh, here. So you have to plug in all these values, right, to do all the calculations. Or imagine, right, if the sample space is 200, then you have to do this 200 times, which is something like very time consuming. But if we can simply use a function to describe the mapping between the realization of this y to the probability, then there are nice formulas, right, to give you the direct answer to the expectation to the variance, right? Okay, so a special case, right? If this n equals to 1, this is just a Bernoulli trial. So for the Bernoulli trial, the expectation will just be the probability of success, right? Because n equals to 1. And the variance will be the product of the probability of success times the probability of failure. Okay, any other questions? Okay, so probably today's talk, the workshop will be a little bit technical, right? But later you will get to have a exciting exercise, so you can get to understand more. Okay, so here. So in R, how can we get to have this binomial distribution? So R, there you actually get to have all these different type of functions related with the binomial distribution. So you see that the binomial distribution is actually controlled by the sample size, right? How many trials do you have small n, and the probability of success, right, this pi or the p. And this d binom, so if you look at this, so in R you have the question mark and the d binom here. So this will tell you everything about this binomial distribution, right? The d binom will just give you the probability mass function, right? Mass. What's the probability that a random variable, binomial random variable, equals to a small value x here? And then this p will give you a probability, right? Which is the probability of a random variable smaller than or equal to a pre-specified threshold. And the q binom will just give you a quantile, that is a cutoff, right? Where the probability is smaller than or equal to something. That gives you this one, right? So if you just specify this probability, it gives you a cutoff here. And R binom will let you to generate a binomial, a random sample from a binomial distribution. Okay, so if you could, for example, you could say I'm going to generate a binomial sample, right? So if you look at this, right? This is how many random samples you are going to generate. For example, I want to generate 1,000 random samples from a binomial distribution. For example, just like the baby example, right? The total number of trials is 4. That is, I'm only interested in 4 babies, and for each baby, the chance of getting a that particular type blood is, for example, 0.2, right? So if you look at this, right, and then if you just type yes, okay, so this is the random samples, right, from that particular binomial distribution, which is in total 4 trials, and the probability of success being 0.2. And so if you look at this table, yes, this is somehow the empirical frequency, right? That is how many times, right, we actually get to sample 0 values. This is about 400 times, and how many times we get to have sample 1 values, right? You see that we only get to have 1 time to have this random variable equals to 4. Is this reasonable? So because I generate this random variable, right, being a extremely small success rate, right? So if you want to have all the 4 babies having that success, right? So in total, the success will be very small. So let's just say, so the question is, what's the probability of y equals to 4? Can you use R to tell me what's the probability of my binomial random variable equals to 4? Where my binomial random variable follows a binom n equals to 4, right? The size equals to 4, and the pi equals to 0.2. We're actually going to use d binom. So the so we are going to use d binom because d binom gives you the PMF, the probability mass function, right? So this x is a realization, right? That is the 4 here. So I want to see what's the chance that my random variable equals to 4, and the size is 4, right? The total, the size, where this size, maybe you are getting confused by the notation. So here, this size is my n here being 4. That is the total number of trials in my for me to define this binomial random variable. And the probability is the probability of success, which is 0.2. Then if you look at this, you see that the chance is actually close to 0, right? So that's why if you look at this table, right, out of this 1,000 random samples, I only sampled 1 variables, right, being 4. Okay, so similarly, if I increase the chance of get success, right, instead of 0.2, I have 0.8, right? So you see that the chance of y equals 4 actually increase a lot, right? So this is really depends on the probability of success. If I have a smaller success rate, then the larger the value of y, the less likely to happen. Okay, so now let's go to the continuous random variable. So similarly, as we defined for the discrete random variable, we also use a function. But here, the difference is that we cannot use this nicer, here, where is it? Nicer like a table format, right, to describe the function, the mapping from the value that y can take to the probability. Why? It's because for the continuous variables, right, they actually get to take countless number of values, right? If it's continuous from negative of infinity to infinity, it's countless, right? So we cannot provide a table to map the y value to the probability. But instead, we are just going to use a function to describe. So again, the property is that for each this function has to be above zero. So you cannot have a function value which is below zero. And instead of summation, right, whenever we deal with a continuous variable, we are going to use integral, right, because we cannot just have a countable summations, right? So it's an integral, and this integral will equal to 1. And again, right, because for the continuous variable, instead of defining a probability, we actually use the area under the curve over that interval. So that means the probability for any interval for y is actually going to be between 0 to 1, right? Okay, so now let's look at the example. So the example is that, so here the population will be individuals who have acquired HIV-associated fungal infection. And the variable we are interested in is the survival time. So if you look at this description of the variable, immediately we understand this is a continuous variable, right? And the random sample is one individual. And then the random variable will just be the survival time, right, for that random individual. So instead of using a table, right, to map between y, the value of y to the probability, now we're actually using a function, right? So this is one major difference. Using a function, and of course you have to specify the range that this y value can take, right? Because this is a survival, so the survival time cannot be negative, right? So the y has to be above 0, and the y is going to be smaller than infinity. So the survival time practice, right? In practice, can be any days, right? Which is greater or equal to 0. And then then if you visualize this function, right, which is if you plot this function on these two axes, well, this x-axis is the realization of this y values you can take, right? And then this y-axis is the function output, right? That is, after you plug in this y value, for example, you plug in y equals to 0, you plug in y equals to 1, you plug in y, let's just say here. So how to look at this, right? So if you, so for example, if this is my function being what's this, 1 over 20, right? Times exp exponential negative y divided by 20, right? So this is your function. And how to draw this curve, right? So you have to specify the possible values for this y. For example, I like my y being sequence from 0. Let me just see how to use this sequence, right? I can specify a sequence 0 from 0 to 100, right? And I just say by equals to 0.1. So if you look at this, right, and you look at the length of this sequence, so actually get to generate 1001 data points, right? And then you just plot, let's see, plot y, and then this is okay. So you specify what's the value of y, and then you draw this, right? And then if you look at the length of this function value, is again. So basically, this is what's the input of y, and then this record output of this function, right? And then after that, you can just plot y versus your function output here. And then this is sort of like how this function looks like on a plot, right? You can see this function, right? How to describe this function, right? This is sort of like just like what we saw earlier, a histogram, right? The plot is this obviously this is a heavy tail, right? Heavy tail towards the right, and then the mass is more concentrated here around zero, right? It's definitely not symmetric distributions, right? So this is how actually whenever you see a function, right, you are not sure what this function looks like. This is how you can plot the function with respect to these input values, just to see what this looks like. And you see that the chance, right, of the frequency, right, of getting y equals to 100 is sort of like zero, right, minimum. So that is if you want to see, right, the probability, for example, y is greater than 80 is close to zero, right? This area on the curve here is minimum. Okay, so this is just a concept, right? Tells you how you can do the probability as well. So here, again, event, the person will survive less than 5 days, right? So in mathematically, how to quantify this statement is that the survival time will be less than equals to 5, right? So this is what we translate from this statement, right, words to the math and to the equation. And then how we can actually compute is that you are going to do the integral, right? The boundary is from 0 to 5, and you just plug in this function, right? And integrate with respect to y. And how to solve it? So you see in R, there's this integrate function. As long as you input this function and then you tell the R what's the boundary, the lower boundary, the upper boundary. So the R will automatically give you this integral value. So the same thing, another event will be the B. The person will survive between 5 to 15 days, right? So how to write out this event is that the outcome, the random variable y, the value of this random variable y will be between 5 to 15, right? And then how to calculate that is that, well, we are just going to change the boundary of this integral, right, from 5 to 15. That is, we are just going to evaluate the area. So once you have this curve, right, and then we specify the boundary will be from 5 to 15, and then this darker area will be the area under the curve, and then this area under the curve will be the probability, right? So this is how we get the probability from a continuous random variable. You have to have this curve, right, this function before first, and then you specify a boundary, right? So in our case, it's 5 to 15, and then you do the integral in order to calculate this area on the curve, and then this is a probability. So last example is a person will survive at least 15 days, right? So that is, we are going to see what's the probability that y will be at least greater than 15. Again, on the same curve, right? First of all, the boundary is from 15 to infinity, right? So you are going to just calculate the area towards the right of this 15, right? Everything towards this to the right of this 15 will be the probability of survival. So the probability of survival is actually going to be close to half. Okay, similarly, once we have a random variable, we are going to find out the expected value of this random variable as a variance. Again, right, before, if we have a discrete random variable, it's summation. So now the summation actually changed to the integral. And the same thing to the variance, right? Before it's a summation, now it's just the integral. Everything else remains the same. Okay, so basically, right, how to find the expected value of the survival time? It's just that we are going to take the integral of y with respect to their PDF, right? The PDF that sort of like the weights, right, associated with each of these possible value of y, and then you take the integral. The r will tell you is 20. And again, if you take the integral of this y squared and minus the expected value to the square, this tells you the variance is actually 400. Okay, so another famous distribution to describe the continuous random variable is the normal distribution, which is also called the Gaussian distribution. Again, the Gaussian distribution is unimodal symmetric, right? It's going to use very, I guess, often for both theory and practical analysis. So for any random variables, right, if they take continuous values, people typically assume they are approximately normally distributed. So here, I guess my question is that, so here, suppose this is how the PDF of this survival time looks like. Do you think we can use a normal distribution to describe this? Is there any way we can do?
I would transform.
Yes. So, well, obviously, the survival time we know, right, sort of like not normally, but right, people attempt to, even though they look at the data, for example, histogram, right, they saw it's heavy tail. This is sort of like commonly occur, right, in clinical studies. So people attempt to, for example, using log transformation or some kind of transformation, right, to pull the tail back towards the center, and then after that they assume, okay, after the transformation, they approximately are normally distributed. So this is all a trick, right? People use before they assume they are approximately normally distributed, right? So in the sense that if the data obviously looks very different from normal, you cannot use normal, right? So this is the bottom line. So in addition, right, in theory, there's a term called the limiting distribution. So that means, well, we are going to talk about this in details later. But here, the limiting distribution of many common distributions, including discrete distributions, are actually normally distributed. So with the condition that the sample size, right, is larger enough. So just to let you know, right, we are not going to go into details about theory here, but just to let you know that the normal distribution is actually one of the most powerful distributions used in statistics. But there are cautions, right, when you use normal distribution. Yeah, any questions? Okay. If you have any questions, just feel free to let me know. Okay, so same thing for the binomial distributions, right? We talk about the binomial distribution. There are parameters associated with binomial distributions, right? For example, if you want to say it's a binomial distribution, you have to tell people what's the value of n and what's the probability of success, right? Otherwise, how can I specify, how can I look at this normal distribution, the binomial distribution? So the same thing for the normal distribution. The normal distribution is actually characterized by two variables. One is the mean, denoted by the mu, and the other is the variance. So this is how the PDF of this normal distribution looks like. Well, again, there's sort of like no intuition, right? It's different from the binomial distribution. This is sort of like just don't have any intuitions for that. But if you look at this term, right, this is just what this looks like is just sort of like doing a standardization, right? You subtract this variable by the mean and divide it by the standard deviation. And so if you look at this formula and after some derivation, we know the mean expect the value of this normal random variable is actually equals to the mean of this distribution. And the variance of this random variable is actually equal to the variance sigma here, which is sigma entered here and also entered into this denominator. So typically, people use big N to denote this is a normal distribution, and the normal distribution is actually controlled by these two parameters. So here is the example which suggests that different parameters, that is different specification of the mean and the variance, will give you different normal distribution, right? So here, normal 0, 1 typically is called a standard normal distribution. The mean is at 0 and the standard deviation is 1. And then this is normal 10, 4. You see that this distribution is actually shift, right? The mode or the center of the distribution is actually on 10, right? And then if you're comparing normal 10, 4 to normal 10, 16, what's the difference? They're actually having the same mean at 10, but you see the tail, right? The blue curve is more spread out, right? Because the variance being 16 is much larger than 4, right? So this tells you the variance actually controls how spread this normal distribution looks like. And then the mean tells you the center, right, where the mode is located. So different mean will help you shift the normal distribution, and the larger the variance will make this normal curve more flattened out, right? Okay. So again, so this is standard normal distribution. Whenever I say, well, let's try standard normal distribution, obviously we know mean equals to 0, sigma equals to 1. Okay, similarly to the binomial distribution, you can also do everything with respect to a normal distribution in R. So again, this DMF gives you the density, right? What's the height? Basically, if y equals to, so here, if y equals to -1, what's the height, right? On this density plot, which is you are going to compute it using D norm. And the P norm actually gives you the probability, right? What's the probability of y smaller than equals to q? For example, what's the probability of y smaller than equals to 15, right? So here you are going to type q equals to 15, and then this gives you the probability. And the Q norm gives you the cutoff point, right? So specify, okay, I want to find out, for example, P equals to 0.5, 25, right? Which is 25th percentile. What's the cutoff point for that, right? So Q norm gives you this number. And R norm, again, gives you the random, right? R corresponding to the random sample, give you the random sample from a normal distribution. Okay, so here, the P norm, actually, if you specify Q equals to -1, right? The P norm actually tells you what's the area under the curve, right? Smaller than or equals to this -1. This is shaded in red. And what's Q norm? Q norm tells you that what if I want the probability being 0.16? What's the cutoff point I have to give, right? So the Q norm gives you this value, the value here. Okay, so probably you are getting, maybe you feel like there are too much things, right, going on. So hopefully this exercise will help you to understand better. So now let's look at the first axis. The first axis is corresponding to the PMF, which is the probability mass function, the discrete random variable, right? So we talk about the example of babies having blood type O blood. So this is actually a binomial random variable. And the number of trials is 4. And suppose the probability of events, right, that is the probability of success is actually 0.44. That is, this random variable, y, the number of success, right, within these 4 babies, is actually a binomial distribution with parameter 4 and 0.44. Okay, so now can you use UR to redo all this analysis? For example, find out what's the probability of 4 babies have type O blood. And also, what's the probability of at least 2 babies have type O blood? And see between 1 and 3 babies have type O blood. Can you use R to do everything? Can you just try, like, do it? Yeah. So I will wait maybe for like 3 minutes and we can just talk about it. Okay, so now let's look at the first event, right? The 4 babies have type O blood. What's the probability that A happens? So first of all, what's the function are we going to use? So let me just go here. By now. So we have actually 4 different type of binom, right? D binom, P binom, Q binom, and R binom. So which one are we going to use for event A? So first of all, the event A, right? All 4 babies have, right? So event A, right? For example, event A, right? Probability Y equals to 4, right? Okay, given this, what should be the correct function to use? Yeah, so basically this is a PMF, right? The probability Y equals to a value, right? What's the probability of that? So this will be D by num. And this X will be 4, right? The value that we are interested to evaluate. And what's the size? Because maximum total number of baby we are looking at is really 4, right? And the probability will be 0.44, right? This is what was specified in the question. So this gives you the probability, right? What that A will happen. Okay, so now let's look at the second one, the B. At least 2 babies have type O blood, right? So let's just copy here. And so that just says at least 2 babies have type O blood. So translate, right? That will be we are interested in finding the probability that Y at least being greater than or equals to 2, right? So how can we get this probability in R? Just using either of these functions. There are actually multiple ways, right? It's just can you think of a way?
Like 1 minus D binom, maybe?
Okay, what she suggests is that it's Y1 minus P by num. Okay, what should I specify the Q here?
Maybe 1, I think.
Maybe 1, and then the other is 4 and 0.44, right? So why do you use 1 minus P by num? So here, what does this P by num mean? Calculate. So the P by num here actually equals to probability of Y smaller than or equals to 1, right? So basically what she says is that, well, the probability greater than or equals to 2 actually equals to 1 minus the complement of that probability, right? So because I know the P by num gives me this, right? The area or right, if you look at the distribution, this is everything occurs below this number. So this is the probability, right? Okay, this is one way to do that. Anything, any other ways we can do? Let me just okay, so we are interested in compute Y is greater than or equals to 2, right? So number one is we can calculate this in terms of magnitude. 1 minus complement, right? What's another way to do that?
Some of the Y equals to 3, 4.
Yes. So basically, right, we can just specify what's the possible values, right, within this interval. That is Y equals to 2 plus Y equals to 3 and plus Y equals to y equals to 4, right? So how to calculate this, right? What's the correct function we should use? Yes. So basically, this is exactly happens, right? This is a d binom. So we are just going to have d binom, which is 2, and then 4, 0.44, right? And plus d binom here. And 3, 4, 0.44, and d binom 4, and then it's 4, 0.44, right? And obviously, right, you can also say, well, the third one would be, right, you can just make this being 1 minus p equals to 0, right? And 1 and minus probability y equals to 1, right? You can also use the d binom to do that. Another way, right, just the fourth way, right, is just you can just calculate this one directly using p binom. How to do that? If I just want to use p binom, not using 1 minus, can I still calculate this directly? So this is actually controlled by the tail, right? So tail tells me the direction. So if I specify lower tail equals to 2, that means this p binom is always gives me probability of y smaller than less than equals to q, right? So if I specify the tail or the lower tail equals to fourth, yeah, see. So this actually let me calculate this greater than q, basically. This is so you can also do it like this, right? So p by no, let me see 1, right? 4, 0 point no. So which is lower tail equals to 4. So we still get the correct answer, right? So remember, this tail is also important, right? Remember, if you don't want to specify the tail by default, that gives you the smaller than equal to probability. If you instead want to get a greater than, then you can either make the lower tail equals to 4, or you can just do the subtraction yourself, 1 minus. Any questions? Okay, so lastly, right, between what's the probability that between 1 to 3 babies have a type O blood? So here, this is our event C. What's the probability, right? So from this event, we know the probability is between 1, right? 1 smaller than equals to y, smaller than equals to 3, right? So in this case, how should we do that? Again, right, similarly, we could say this equals to p y equals to 1, right, plus p y equals to 2, and plus p y equals to 3, right? And then this just means I can use d binom, right? So this means here. So this means I can just use d binom. Okay, so if instead of use d binom, I want to use p binom, how can I do that? Can I say probability y smaller than equals to 3 and minus 1? So this is probability y smaller than 1, right? So this is just equals to probability y smaller than equals to 3 minus probability y actually equals to 0, right? Remember, this p binom is always like smaller than or equal to has the including the chance of equals to this q. Right. Hopefully, from this exercise, you understand better about this d binom and the p binom. Okay, so can you maybe just quickly compute the expected value of this y using this binom function? How to do that? Right, so according to the definition, expected value, right, you are going to actually compute the sum of all the possible values of y and multiplied by the probability of this y equals to exactly this value, right? So according to this, we could write the mu expected value actually equals to all the possible values, right? 0 times d binom, right? Which is 0 and 4, 0.44, right? And plus 1 times d binom, right? The weight, that is how likely this value will occur, right? And you do that for all the possible values from 0 to 4 and plus 3 times, and you do 4 times. And if you look at this mu, right, this is 1.76. And if you compare this with the theoretical value, which is the number of trials times the success rate, again, they equal, right, 1.76. So similarly, right, you can take the square for each of these values and compute this expected value of y squared, right? And then I derive for the variance. Okay, so similarly, right, the other example we use for the survival time is actually exponential random variable. So this is EXP, stands for the exponential distribution with the parameter controlled by lambda. So the lambda equals to 1 over 20. Well, can we, for the time being, let's just look at the example here. The person will survive less than 5 days. How do we do that? So again, if you are not sure how to use this R function, we can, so this is exponential distribution. Again, you have this D exp, P exp, Q exp, and R exp. So here, the person will survive less than 5 days, right? What this means is that we are actually interested in probability that this exponential random variable y will be smaller than 5, right? Okay, so I guess my question is this probability equals to probability y smaller than equals to 5? Are they equal or not?
This is going from 0 to 4, and that is going to 35.
Okay, so this is actually not different, different, right? So it doesn't equal to this if y is a discrete random variable. So these two things are actually equal if continuous random variable. Why? Because for the continuous variable, we are calculating the difference, right? Because the difference is only what's the value for y equals to 5, right? So what's the value for y equals 5 if y is continuous? So this is 0 if y is continuous random variable. Because the area under the curve, right, equals to 0, right? Because you only have a straight line, right? What's the area? The area is 0, right? The area on the curve is equals to 0. So that's why for the continuous distribution, it's okay, right? Sometimes you write y smaller than 5 or y smaller than equals to 5 because the probability will always be the same. But there's a significant difference when the y is discrete random variables, right? Because the probability of y equals to 5, right, may not be equal to 0, right? So just to let you know that. Okay, so in this case, how can we calculate the probability of y smaller than 5? Which one, DEXP or PEXP or QEXP? Because REXP is just a generate random sample, right? So I guess for the three functions above, which one should we use? Yes, because the PSP is always calculate this, right? Doesn't matter y is discrete or continuous. PEXP is always calculate y smaller than or equal to a Q value. So we do PEXP, and then Q specified to be 5, right? And this is 1 over 20. So this is a probability that y is smaller than 5. Okay, so I will just skip all these two exercises. Hopefully you can practice this later. And I will just quickly go through this before we take a break. So the QQ plot for checking normality, right? So I mentioned about the normal distribution is a very common assumption, right? To do a statistical analysis, to do theory. But you may ask, right, how can I verify, right, these random variables normally distributed? You just, for example, plot the histogram to check whether they are bell-shaped, right, symmetric. But then there's a more sophisticated way to do that, which is using the QQ plot. Have you heard of QQ plot before? Yes, right. You probably heard of that. So basically, you are going to look at the QQ plot. For example, if I generate a random variable, this is R norm, right? Instead, let me generate a random variable from exponential distribution. I'm going to generate 1,000 random variables, and with rate being 1 over 20, right? For example, then if you look at this histogram, obviously you know it's heavy tail, right? And another way to look at this is just you call QQ plot, and then this DF. QQ no. Sorry. This is QQ norm, right? It's QQ norm DF, and then you are going to follow by QQ line DF, right? So basically, what this tells you is that we're actually comparing, if you look at this x and y axis, it's theoretical quantile and sample quantile, right? So ideally, if my sample, like those quantile, that is sample statistics, they are actually, if my sample follows a normal distribution, then my sample statistics will actually match with my theoretical statistics, right? So I would expect those dots will be lying on this straight line, right? But now we see that these black dots actually deviate a lot from this straight line. That means I know my sample is actually cannot be safely quantified by normal distribution. So basically, this is like how you are going to look at this normal QQ plot, right? Just to see whether there's any significant deviation, right, on this dot with respect to this line. Again, right, similarly, if I generate my data from my normal distribution, let's just say R norm. Again, 1,000, I just generate this from the standard normal distribution, and I just do QQ norm and QQ line. Yes, you see, if my sample is truly a normal distribution, you would see, well, they fall largely on this straight line. So this is where you say, well, providing this normal QQ plot, we can safely assume that the data follow a normal distribution, right? Okay, so I will stop here, and so this is let's start at 10:50. Is that okay? Yeah. Okay, so let's start. Okay, so now let's talk about the second part, which is the parameter statistic and sampling distribution. So hopefully for this part, right, this will actually naturally connect the distribution to statistical inference so that you can could have some better ideas in terms of why we're going to use distributions and how we are going to use samples to make inference to the population, right? Okay, so before we do that, let's look at the definition of what is sample statistics. The sample statistic is any value computed from a sample, right? So you can have a sample mean, sample median, sample standard deviation, etc., right? All the summary statistics, all the summaries you learned at the previous class, right, can be used as a sample statistics, right? There's maximum, minimal, IQR, they can all be sample statistics. And the counterpart of this is actually the parameter. The parameter is actually with respect to the population, right? When we talk about the parameter, we actually talk about the population parameter. And then the population parameter is actually the thing we are really interested, right? Because understanding the population parameter, it can help us to quantify what this population looks like, right? For example, if I know the population is so like normally distributed, right, and the population parameter is the mean, right? So if I understand what this population means, whether it's 0 or 10, right, this will really tells me the information what I'm interested, right, or the population variance, etc. So we're actually going to use statistics, right, computed from the sample to make an inference on the corresponding population parameter. This is what we mean by inference, right, the statistical analysis. Okay, so for example, case one, a researcher wants to know the mean change in LDL among the target population, right? The mean change in the population is actually our population mean, which is the population parameter, right? The thing that we will never ever get to observe, right? Because we can never afford to measure everyone in the population. If we can measure everyone in the population, then we don't need statistics, right? We can easily get the population mean just by sum this up and divided by the total, the sample, the population size. But instead, we are going to do a random sample, right? We are going to randomly sample 300 individuals from the population and calculate the mean from this 300 individuals, right? And we would say, well, this is the sample statistic, which is the sample mean. And how to make the connection between sample mean and the population mean is that we are going to do inference, right? We are going to do statistics. So one way is that I can simply use this sample mean as my estimate of my population mean, right? I don't know what my population mean is, right? But once I have the sample, I have the sample mean. And my assumption is that I do this random sample well enough. So this random sample is a good representation from my population mean. So that's why I can say, well, the sample mean is actually give a good estimate to the population mean, right? So this is how we do inference. And similarly, right, a researcher wants to know the preference of virologic control among a target population, right? Because remember, this virologic control is a binary 0, 1. So the population mean is actually a population proportion, right? Well, that is, what's the proportion of the population that is under this control, right? But instead, I'm going to sample 320 individuals, and I'm actually going to count how many have this control, right? That is the sample proportion, which is a sample statistic. So this is the sample version of the proportion, right? And versus the population proportion. Again, I could do the simple statistics, right? The inference, meaning that I'm just going to say the population proportion actually equals to the sample proportion, right? This is one way I could do the inference from the statistics to talk about what this population looks like. Okay, so now mathematically, right, connecting the population mean, well, the population mean is actually the expected value of a random variable y, right? And typically denoted by mu, right? And then there's sort of like no randomness, right, in the population parameter, right? It's just a fixed value. And the same thing for the population variance, right? It's a variance of this random variable. And we can also have this population percentile, right? You can think of this population median, the 25th percentile, 75th percentile, etc. But statistics, right, especially the sample statistics, they are random variables. Why are they random variables? Because the statistics is any summary from the random sample, right? You think about the random sample, that is, if you repeat this sampling procedure multiple times, right? For example, the sample mean will always be different, right? Because you will always include different elements from the population into the new sample. And you calculate anything from this sample, it's a sample statistic. And this sample statistic will have different values, right? So which means it's a random variable. So the statistics are random variables, and the random variables, right, will have probability distribution depending on whether it's discrete or continuous. So they will have either PMF or PDF, right? And so the statistics will have those probability distributions. Okay, so the distribution related with statistics is actually called a sampling distribution. But again, right, the sampling distribution, as the name suggests, is just a distribution. It is either a PMF or PDF of these statistics, right? So the most, I guess, the commonly used statistic is just a sample mean, right? So you can have a white bar to denote this is a sample mean. And we typically use S squared to denote this is a sample variance. And we use big M to denote this is the sample median. And well, the distribution, right? Because the sample mean and the sample variance and the sample median, they are just the statistics. And we know the statistics are random variables. They have distributions, right? So any distribution related with those sample statistics, we simply call them a sampling distribution. It's just another terminology, right? Differentiate between the focusing on this is really the distribution summarizing the quantity, right, of from a random sample. So we use big Y to denote a random variable, right? So Y1, Y2 to Yn is just be a random sample, right, from some distribution of interest. And remember, a realization of this Y is denoted by small y, right? So you have a random variable. After you perform this random sampling, you get to see what this value looks like, right? So this is what we mean by the realization. And the standard error is just the square root of the variance. The standard error is just a standard deviation of the sampling distribution. And the standard deviation is a general measure of the spread about the mean, right? Or of a sample or a population. So for example, once you have the sample mean, you have the sampling distribution for this sample mean. You can also use this standard deviation, right, of this random variable to quantify what's the standard error of the mean or the standard error of the variance, etc. Okay, so let's go to this sampling distribution of the sample mean, right? Because we typically, right, the most important thing we want to quantify is just the central location of the variable we are interested in, which is the population mean. So that's why whenever we have the sample, we are going to calculate the sample mean. And once we have the sample mean, we want to use the distribution to quantify this sample mean, right? So what's the sampling distribution of this sample mean? That is when you repeat this random sampling procedure multiple times, you will get different sample means. And then what's the distribution of this sample mean? So this is actually what I was talking about. So here, suppose I want to draw 100 random samples from my population, right? I can do it once. This is S1, right? I'm going to do the sample once. This is my the 100 draws from this population. And from this 100 draws, I can generate a sample mean, right? Basically, just taking the average of all these readings. And this is my Y1 bar. And I can repeat this sampling 500 times, right? So for each time, I will generate probably a different values, right, or the realization of these 100 random variables. And then I get to compute the random samples for these 500 draws, right? So my sampling distribution is actually the distribution of this Y1 bar, Y2 bar, Y3 bar, etc. to Y500 bar. What this distribution looks like. Does that make sense? Okay, so maybe, right, let's just do it in R, right? So you can have a better idea what I'm trying to do. Okay, so I'm going to define, right, how many samples I am going to draw, right? Suppose I say S equals to 500, right? I'm going to generate those random samples 500 times. And what's the sample size, right? For example, this is the sample size for my random sample, right? So each time I'm going to draw randomly 500 elements from my entire population, right? So suppose my population, right? My population is a binomial distribution with maybe sample size 4, right? And then the number of trials is 4, and the probability of success being 0.44, right? So what I can do is that, for example, just say I can do a for loop, right? For S equal 500, right? Can I? So this is, I'm going to do this random sampling 500 times, right? For each time, I'm going to generate a random sample, right, from the population. Draw 100 elements. Draw 100 sample from my population, right? So my data will be from R by norm. I'm going to draw 100 sample from my population 4 and 0.44, right? So for example, if I draw this once, length. So you see, I'm actually generating 100 data, right? And then actually, because we are talking about the sampling distribution of my sample mean, that is, well, instead of looking at my sample, I'm going to record my sample being Y bar, right? So I'm going to have a Y bar. Y bar being my sample mean, right? Sample mean. And which is a vector, right? Rep 0, 500, because I'm going to record the sample means from my 500 random draws, right? I do this 500 times. So this is my Y bar. The S repeat is actually the mean of my DF, right? So I'm going to generate a random sample 100, and I'm going to calculate my sample mean, right? And I'm going to repeat my procedure 500 times, right? So this is what I'm trying to do. Okay, let me see whether it goes through. Okay, so if you look at this Y bar, so this is actually the sample mean, right? After I repeat the procedure 500 times. And if you look at this histogram of my Y bar, what do you think it looks like? It's sort of like a bell shaped, right? Sort of symmetric, and we can use what we learned just a few minutes ago, QQ norm, right? Y bar and QQ line, Y bar, right? So you see that they actually pretty close to this straight line, right? So this is what we mean by the sampling distribution, right? Which is the distribution for this sample statistics. While in our case, the sample statistics is the sample mean, right? how can we get to have the distribution of the sample mean? Is that imagine we are going to repeat this random sample lots of times, right? Then we will have a distribution for that. So this is what we mean by the sampling distribution of the sample mean. And then the standard deviation will just be, the standard error from this sampling distribution, right? To quantify how different those sample mean we get if we randomly draw 100 samples from the population. Right. So obviously, what the theory says that if we repeat this multiple times, right, for each this sample, right, the sample mean, if we do the inference, right, this sample mean will be actually very close to the population mean, right? So this is what this approximation equals to, right? If we take the mean of this each sample, right, the mean of this. So if I say the mean of this y bar, right? And if we know the population, right, the population will be 4 times 0.44, right? So you see that the mean of my x bar is actually 1.658. You see that it's going to be very, very close to 1.76, right? So this is actually what our part of the inference is, right? If we repeat this procedure multiple times, right, we take the mean of each sample, and then the mean of those sample means, right, from 500 repetitions is actually going to be very close to the population mean. And the same thing, right, the variance, right, S squared actually computed from those sample statistics will be actually very close to the population variance and divided by the sample size, which is the 500, right? So this is part of the inference, how we are going to do that. Connect the sample statistics to the population parameters. And then there's a famous theorem associated with this observation, right? And you see that, doesn't matter, right? You see my population is actually a binomial distribution, right? It's a discrete distribution. But then if you look at my sampling statistics of my sample mean, they actually looks very similar to the normal distribution, right? And then if you look at this histogram, they are actually a continuous variables, right? Because the sample mean from this binomial distribution is actually a proportion, right? Which is sort of like continuous, right? So in general, right, this just says the distribution of my random sample. Well, in my case, the distribution of my random sample is a binomial distribution, right? But then after we observe the sampling distribution, right, of my sample statistic, which is my sample mean, they don't look the same, right? One looks like a normal distribution, the other is actually a binomial distribution. So that means the distribution of my random sample and the sampling distribution of the mean is not necessarily the same. So you can use QQ plot, right, to see as an exercise to see. We actually did this exercise, right? We look at the binomial distribution and the sample mean, right? The distribution is actually follows a normal distribution. So here, this is sort of like the theorem, right? The central limit theorem. In the word, it says if a random variable y has population mean mu and non-zero variance sigma squared, then the sample mean y bar based on n observation is approximately normally distributed with mean mu and the variance being sigma squared divided by the sample size for sufficiently large sample. So basically, what this means is that the sampling distribution of my sample mean, which is y bar, is actually normal distribution, right? Basically. So this is just to give you an example where this is my distribution for my random variable y. My random variable y could be from standard normal distribution, could be from exponential distribution, could be from Bernoulli distribution, or could be from chi-square distribution, right? They can be either the same as normal or different from normal. And then when you do generate the sampling distribution of your sample mean, you always see the normal type of curve, right? The symmetric bell-shaped distribution, right? So it doesn't matter the original random variable is generated from normal distribution or not. So this is the sampling distribution for the sample mean from the chi-square. This is sampling distribution of the mean from the exponential, and this is from the Bernoulli. They all look like a normal distribution. So this is what this theorem says, right? Whenever you have a sample, doesn't matter where the sample is drawn from, right? The sample mean is always approximately normally distributed. Yeah. And also, again, right, you can use this QQ plot, right, to verify the sampling distribution is always approximately normally distributed. Doesn't matter where this y, the original distribution of the y is from. Okay, so now you might ask, right, what is considered sufficiently large? So obviously there's no strict cutoff to be, you have to have your sample size greater than, 100 or 1 million, etc. But it really depends on how this distribution looks like, right? So if the y, right, the random variable you are interested, it has either discrete distribution or heavy tail distribution, which looks very different from normal distribution, right? Then obviously the larger the sample size, the better. On the other hand, if the y is already follows a normal distribution, right, then probably you can have at least 30 sample size sufficiently large enough. So basically, there's no, a clear cutoff being what is sufficient large, but you have to remember, right, as larger the sample size is better, right, to have a approximate normal distribution. Do you have any questions? Okay. So now let's look at some exercise, the sampling distribution. Okay, so it asks you to create a matrix of size 100 times 50 of data generated from a normal distribution with some mean and some variance. So you can specify what the mean is and what the variance is, right? You can specify the mean to be 0, to be 10, or whatever, right? And the variance, but obviously the variance has to be a positive number. Or you can simply say it's from a standard normal distribution. And it asks you, first of all, to generate a matrix which was from this independent field with the random variables generated from a specific normal distribution. Can you do that? So basically, this question, right, is the same thing as what I just wrote here. It's just for what I did is I use a for loop, right? But here, this question asks you, instead of for loop, just put this everything into a matrix, right? So I could say my data is a matrix, right? Matrix. And what's the element? Because it asked me to have 100 rows and 500 columns. So the total number of elements will just be 100 times 500, right? And this element will be generated from a normal distribution, right? R norm. Sorry, no. So instead of doing this, right? So I'm going to have a matrix having these many elements, which is 100 times 50, 500. And I'm just, for simplicity, I'm just going to generate these number of samples from a standard normal distribution, right? And then I'm going to rearrange this matrix so that the number of rows equals to 100, right? So if you do that, size, R, are known. Okay, so if you do that, right, and then if you look at my dimension of my DF, which is a matrix, right, 100 rows and 500 repeat, right? So basically, 100 is my sample size, right, and 500 is the number of repeats, right? I'm going to repeat this sampling procedure 500 times, right? And each time I'm going to generate 100 data points. And then you are going to compute the mean of each sample, right? So that is for each 500 columns, right? I'm going to compute the mean, right? For that 100 sample. So how to do that? So I'm just, which is y bar, right? Will just be the column means of my data frame. Let's just see. So if you look at this length of y bar, it's actually 500, right? So this is, I'm going to get 500 sample means, right? From, so first of all, once I have this, right, you can look at the histogram of my y bar, which is my sampling distribution, right? And then you can check, right, the sample mean of my y bar. Is this close to zero? It's very close to zero, right? Because my population is generated from the standard normal distribution, so the mean is zero. And then the mean of my sample mean is actually very close to zero. Then you can also look at the variance of my bar. My variance of my y bar, right? And if you look at the population, my variance is 1, right? So I use my y minus divided by the sample size. You see, they are actually very close as well, right? The variance of my the sample of my sample mean, right, is actually equals to my population variance divided by the sample size, right? So this is a way to help you to verify the central limit theorem, right? And also instead, right, you can also change this to exponential distribution, right? You can change to exponential distribution with rate 1/20, right, from the example. And then you can also, which is very close to the mean, where the mean is 20 here, according to the formula for exponential. So this is 19.97, and then this is my 20, right? Okay, so now what if, right, let's just say instead of 100, I'm going to reduce my sample size to be just a 10, right? Just to see, okay, what if I have a small sample size? Instead of 100, I will just do 10. And also, this is actually generated from a distribution which is different from normal, right? Exponential distribution. Well, I mean, for this case, right, you see that the difference, right? The difference is actually a little, so the previous one is much closer to 20, right? So here we actually have a little bit error, right, in estimating the true population mean. Right, let's just say binomial. We can do some exercise and just say 4, right, 1.2, and let's see. This is my y bar, right? And if I do this 100 times, let's see what will happen. So it's closer, right? And I can do, okay, never mind. Okay, so this is all a simulation study just to show you what's the property of the sampling distribution to my sample mean, right? So that means once, right, you have this nice property, right? Where is it? The sampling distribution here. So this is our theorem, right? That means once we have this defined, so whenever you have a sample, you don't actually need to physically repeat this sampling procedures 500 times, right? You are just going to have one random sample, right? And then use this theorem to do some inference, right? So in reality, you are going to skip this 50, right? You are just going to draw a random sample of size 100, right? And then the sample mean will follow a normal distribution. Does that make sense? But this simulation, I repeat this multiple times just to see empirically, right? If you generate this random sample many, many more times, the sample mean is very close to the population mean, right? Okay, so why do we want to have the sampling distribution of the sample mean, right? So first of all, right, from this sampling distribution, right, we know we can somehow make a inference about population mean, right? Basically, the mean of this sampling distribution is actually equals to the population parameters, right? The population mean. But well, this is there's a different, right? This is called in statistics. This is called the point estimate, right? I'm going to use, for example, a sample mean as my estimate of my population mean. This is called point estimate, just a single number, right? So, for example, this actually estimate that it will rain at 3 p.m. Is this going to really happen strictly at 3 p.m.? Probably not, right? Probably it will occur sometimes maybe slightly before 3 p.m. or slightly after 3 p.m., but always centered around this 3 p.m., right? So this is what we mean by the point estimate. But if you want to gather more information, right, what's the range, right? Well, obviously we know high chance is at 3 p.m., but there's always another chance to be a little bit different from 3 p.m. So this is called the interval estimate, right? You probably heard of the confidence interval, right? So it's always like whenever you provide a point estimate, people tend to provide the confidence interval, right? An interval estimate associated with this point estimate. Right, the interval that these people provide is actually, it will actually run any time between 1 p.m. to 5 p.m., right? So, well, obviously, if someone says, I am going to estimate, right, the interval is from 1 p.m. to 5 p.m., and the other is actually, after another procedure says, well, the rain is actually going to occur from 2 p.m. to 4 p.m., right? So which interval do you prefer or contains more information? What do you think? One is from 1 to 5 p.m., the other is from 2 to 4 p.m. Small, yeah, you want the interval to be as small as possible, right? For example, in the dream case, if this interval actually coincides with the point estimate, right, that probably says it's really going to happen at 3 p.m., right? So obviously, if the interval is, well, instead of in the extreme case, right, if the interval is actually from midnight, right, to another midnight, right, the whole day, right, 24 hours, right, you probably wonder what is the point estimate really useful, right? That means it can happen anytime, right? So this actually, the confidence interval can also actually tell you maybe how confident, right, this point estimate is really is, right? Okay, so the reason that we are going to derive, or we actually first of all derive this sampling distribution to the sample mean is that from this sampling distribution, we actually get to construct the confidence interval, right? So, well, again, I'm going to skip all the details, right? But this is sort of like the confidence interval, the formula that people use if the random variable y is actually from a normal distribution. Well, obviously, the normal distribution, you think of this, right? It's a distribution, and the mean, mu and sigma square, is the population mean and the population variance, right? And they are unknown, right? And then the confidence interval for that population mean, well, the sample is generated from a normal distribution, is actually constructed from this. Well, this y bar is the sample mean, and S is the sample standard deviation, right? When you collect sample, you can calculate sample standard deviation. and you divide it by the square root of this sample size. So here, what's more important is this one. Is this t, which is a constant, right? The constant, what this t means is a quantile from a t distribution with n-1 degrees of freedom. So have you heard of t distribution before? Yes, right. So t distribution is similar to the normal distribution. The only difference is that the t distribution has a heavy tail, right? It has one parameter called the degrees of freedom. So the smaller the degrees of freedom gives a heavy tailed t distribution, right? So for example, if I set my degrees of freedom for the t distribution to be close to infinity, that means this actually going to be a normal distribution. So the larger the degrees of freedom, the more closer to the normal distribution. So again, right, so this is actually the quantile. So this actually utilizes a Q function in R, right? Just like Q norm or Q by norm, this quantile, right? Remember the Q stands for the quantile. So you specify a probability, right? Remember the t distribution is continuous. So this is the area under the curve, right? The probability, that is the probability, my random variable, right? Smaller than or equals to or smaller than a some value. The probability is actually equals to 1 minus alpha divided by 2. So this is associated with hypothesis testing. You are going to get to know more about this alpha for the next part of the workshop. But here, people typically set this alpha to be 0.05. So you specify this probability. This gives you the quantile for this number. So once you have this number, you can plug in everything to construct a confidence interval. Okay, so this gives you how this t distribution looks like, right? You see, this is a t distribution with degrees of freedom 1, and then this is a t distribution with degrees of freedom 10, right? So you see, with higher degrees of freedom, this t distribution looks more similar, right, with respect to the normal distribution. And then if you have a smaller degrees of freedom, you will have a larger tails for the t distribution. Okay, so now let's look at the example. How can we actually compute for the confidence intervals, right? You can compute, sorry, I should say that this alpha, right, controls the width of your confidence interval, right? Suppose alpha equals to 0.1. So this will give you 90% confidence intervals, right? So it asks you to compute 90% and 95% and 99% confidence intervals, right? So for example, for the 90% interval, what's the value of this alpha?
0.1.
Yes, 0.1, right? So you immediately know the alpha equals to 0.1. Okay, so, well, this is actually related with the data, right? So this, we have a data. Let's just suppose, right? We have let's just do a small exercise. Suppose our sample mean, right? X bar is 10, right? And what else do we need? And this, right? The sample, the F sample standard deviation is 0.1, right? Okay, and we know alpha equals to 0.1, right? Can we construct 90% confidence interval? Suppose the random variable is from the normal distribution. That is, we are going to use this formula. Can you construct that based on this is our summary statistics? X bar meaning the Y bar, I should say Y bar. Right? Can you quickly compute and tell me what's the confidence interval for that? So I should say the sample size, right? Suppose the sample size is 10, for example. So we can just follow the formula, right? So first of all, we are going to calculate the left limit, right? Which is y bar minus, right? There's a constant, for example. I would just say constant, right? And times the s divided by the square root of my sample size, right? Right, so this is according to the formula, right? Y bar plus minus a constant times s divided by the square root of the sample size. So what's unknown is actually because we know y bar, we know what's the sample standard error, right? And we know the sample size. What's left is this constant, right? How to calculate this constant? The constant, right, is the percentile, right? What's the cutoff, right, for that t distribution with degrees of freedom 9? So the area towards this left equals to 1 minus 0.1 divided by 2, right? Basically, this is what we are trying to compute. How to compute that? Basically, we want to compute for Qt, right? Which is Qt. If you type Qt, right? This tells you help you to calculate that specific quantile. And then Qt followed by the probability, right? The probability from the formula is 1 minus alpha divided by 2. So you can type 1 minus alpha being, I would just say alpha divided by 2, right? And then for the t distribution, there's a degrees of freedom. And then the degrees of freedom is n minus 1, right? Which is still n minus 1. So if you read everything in R, let's just say the constant. What's the value for this constant, right? This is the value for this constant, right? So you see, this is actually different from what you see here. Why? Right. This is my lecture note tells you, right? According to the formula, this constant equals to 1.651. But from our calculation, we actually get to have 1.833. Is there anything wrong with our formula? Then why we have different numbers? Yeah, there's something wrong. What's wrong?
Oh no, I agree with you.
You agree with me? What?
Well, I mean, we did a random sample, so the value could be different.
Yes. Well, partly yes, but remember, right? Even we actually use the same number for this alpha. Remember the t distribution. Another important characteristic of t distribution is the degrees of freedom. So in this exercise, the sample size is definitely more than 10, right? You remember we actually, for this case study, it actually have 300 samples, right? The sample size. But here for our sample size is only 10, right? So that's why we are working under the different t distribution. So that's why even though the alpha is the same, but the constant you get is actually can be very different, right? So that means this constant is actually will be influenced by the sample size, right? So this just remember. So that's why our constant, right, is different from what you get from this exercise because they have very different sample size. Their sample size is 300, ours just 10. And well, let's just say this is my constant equals to this, right? Here. And then, so this is my lower boundary, right? And I have my upper boundaries being y bar plus this constant, right? Oh, I didn't have the constant. So this is my lower and this is my upper, right? So this is actually my confidence interval, right? So that is right. Once you have this sample, First of all, according to this formula, right, if you want to construct a confidence interval for this population mean, what you are get is that you are going to first of all compute the sample statistics, right? We are going to have this sample mean, and we're also going to have this sample standard deviation. And most importantly, we're also going to know what's the sample size, right? And with all this, right, you are going to, so this alpha is actually determined by yourself, whether you want to have a 90% confidence interval or 95 or 99% confidence interval, right? It's up to you to decide. But here, Y bar S and small n is actually associated with your sample. Once you have a sample, you should be able to compute all this, right, and get to the quantity, the confidence interval. Okay, similarly, right, if you want to compute the 95% confidence interval, the same procedure, right, because you are always compute something on the same sample, it's always the constant will get to change, right? So before my alpha is 0.1, so if I'm working with 95% confidence interval, what's the alpha value?
0.05.
The what?
0.05.
So this will be my alpha value, right? So everything else becomes the same because the sample mean, sample standard deviation will be the same, right? Because you always only have this particular sample. It's just this constant will get to change, right? So before it's 1.8 something, now it gets to be 2.26. And then with this new confidence interval, the constant, right? So this is your confidence interval, right? Okay, so the same thing, right? So it's similar procedures, right? You're just going to stick with the formula, right? Choose the right formula. If you know the underlying distribution for your random variable roughly follows a normal distribution, you are always going to use this formula to construct a confidence interval. This is a confidence interval for your population mean. And the estimate, right, the point estimate for your population mean is actually the sample mean, right? So this is how you do inference, right, using your sample. Okay, so now how to make interpretation of these confidence intervals, right? Again, just like we do those repetition of the random sample, right? If you repeat this random sample different times, right, the confidence interval you compute will always be different, right? Why? It's because whenever you redraw another set of random sample, the sample mean will always be different, right? And even though the same sample size, then the Y bar will always be different. The X will always be different, right? If you have this being different, so that means the confidence interval you constructed will always be different, right? So before I go into this details, this is sort of like replicates, right? The way you can think about the confidence intervals, right? The same thing. This is a confidence interval. Suppose these blue lines are our population mean, right? And obviously, we don't know the population mean is actually equal to 2. What we get is that we are going to randomly draw a sample from this population. And then this is, I'm going to do this random draw 80 times, right? I'm going to repeat this sampling procedure 80 times. And for each replicate, right, I can construct the confidence intervals, right? Because I am actually having the random sample, my sample mean, sample standard deviation are different. So you see that the random, the bars, right, which is the confidence interval, their locations actually get to shift, right? So this is the behavior of my confidence interval. This is really depends on your random sample, right? Different people having different random sample, of course, they are actually having the different confidence interval. Okay, so in this case, how can we actually understand, interpret this confidence interval, right? So that's why, right, this people typically call this as a frequentist approach, right, to look at statistics. That is, we are looking at the frequency, right? If you do this multiple times, what's the frequency, right? Basically, that is actually that is if I do multiple times, right? That is 80 times. What's the frequency of my constructed confidence interval that will actually cover the true population mean, right? So you see that the red line actually are the confidence intervals I constructed that actually miss the population mean, right? So this is the frequency. I will have extremely low frequency, right? If I just do this multiple times, I will have extremely low frequency that my constructed confidence interval will miss this true population mean. But most of the time, for example, 90% of the time, right, empirically, right, frequency 90% of the repetition, right, will actually, the confidence interval I constructed will actually cover this true population mean. This is how we understand this confidence interval. Yeah, so right, so this is if we draw multiple samples, right? If we repeat the procedure multiple times, compute a Y bar, compute S, and then compute the confidence interval, then about, suppose alpha equals to 0.1, right? Then about 90 of the confidence, the intervals will contain this population mean, right? So this is a frequency interpretation of the way that we construct the confidence interval. So, but in common practice, right, people tend to, when you construct a confidence interval, then people will tend to say that we are actually 90% confident that my single interval, the way that we constructed, actually contains the population mean, right? This is another way, maybe it's more easier to understand. But sometimes people make a mistake about putting this probabilistic statement on the population mean. Remember, when we talk about population, doesn't matter if it's a population mean or population variance, as long as the parameter associated with the population is a constant, right? It's a fixed value, right? If you have already defined a whole population, the population mean will never change, right? For example, if we are doing if it's time independent, right? The population mean is always 2, for example. So there's no probabilistic statement you should ever put on the population parameter, for example, population mean, right? You shouldn't say that, well, there's a 95% chance or probability that the population mean is between this and this, right? The population mean is a constant. It's always the probabilities with respect to the confidence interval, right? You should say there's a 95% chance my calculated confidence interval, right, will cover this true population mean. Yeah. So just to make sure, right, you don't write something another way around. Okay, so obviously, right, things can get complicated when the random sample is not following normal distribution, right? Even after you do transformation, and it's still not a normal distribution, right? So in this case, we cannot use the formula, right? Remember, the formula that you construct the confidence interval has a criteria, that is, has assumption, right? That is assuming this random sample follow a normal distribution. If, for example, they are following a binomial distribution or any exponential, right? So you cannot use that, which is the constant is computed by a t-distribution. But instead, you are going to use a z-score, which is, this is the quantile computed from the standard normal distribution. So if, for example, if I want to compute, for example, my constant, right? So, for example, if I want to compute the constant, right, which is the quantile from my z, which is the standard normal distribution with probability specified by 1 minus alpha divided by 2, right? So the way I can compute, right, because I just use Q, right? But we know this is a normal distribution, and in fact, it's a standard normal distribution, right? So you have the Q norm. So this is your Q norm, right? you see default is already mean 0 and standard deviation 1, so you don't really need to specify mean and standard deviation again. But rather, you just need to specify the probability, right? The probability is, again, my 1 minus alpha, right? So if I say alpha equals to 0.1, so this is actually my new constant, 1.64 or 65, right? So you see that for this one, because this is a normal, right? And then this is a standard normal. So what this means is that doesn't matter what's your sample size, right? The constant is always the same as long as you specify the same alpha, right? So you see, different from Qt, you have this degrees of freedom, which is a function of the sample size, right? So in this case, this will always be the same, right? The same. This constant from the Z distribution, the standard normal, will be the same for different sample size, right? As long as the alpha is the same. Right, so for anything that is non-normally distributed, so the confidence interval, or rather the central limit theorem, will give you this formula. Everything will be the same. You are still going to compute the sample mean, sample standard deviation, and you still need to find out what the sample size. It's just when you try to compute the constant, instead of using t distribution, you are just going to use the standard normal distribution. That's it. Right, so this is the same case study. So, well, in this example, right, my random variable y1 to y262, they actually follows a Bernoulli distribution, right? It's a binary because I have this inequality here just to see whether the change in LDL is satisfy this criteria. If it's yes, then it's 1. If it's no, then it's 0, right? So definitely it's not a normal distribution. Even after you do any kind of transformation, right, it's going to be not a normal distribution. So what you are going to do is that once you have the sample, you are just going to calculate the sample mean, which is in this case the sample proportion, right? And then check for the sample standard deviation, which is the proportion, right? The proportion of success times the 1 minus the proportion of success, which is the failure, right? And then you plug in this formula, right? Then you get to have the confidence interval for the population proportion, right? So given this confidence interval, how can we make an interpretation of that? So for example, once you derive this, right, you have to tell people what this confidence interval means. Yes.
We are 95% confident that that interval will contain the true proportion.
Yes, the population proportion, yes. But you can't say, right, we are 95% confident the true population proportion lies within, right, because it's a constant. There's no probability statement associated with the constant, right, because it's always there, right? Just so this is all a common mistake people typically interpret the confidence interval. Yes, just to summarize, right, before we end the workshop, today's workshop. So when there are two different scenarios, right? If the underlying population is normal, you are going to use this t distribution to compute the constant, right? If anything else, you are going to use this z-score to compute, which is from the standard normal distribution. But for any case, you are going to compute the sample statistic y bar s and get to know the sample size. Okay, I guess that's everything for today. So for the next 3 workshops, there will be another faculty to talk about that, and then I will come back to teach the last one, which is bring your own data, right? You can ask me any questions. There will not going to be any lectures for the last part of the workshop. Okay, thank you.